So in this lecture, we're going to talk about the Bernoulli equation. Before we do that, let's going to review a few things that we left over from the energy, conservation of energy. We define the mechanical energy. We can define it as follows. This is the density. This is the pressure divided by the density plus v squared divided by 2 plus g, that's gravitational constant, and this is the distance z. Okay, so this term represents the flow energy. This represents the kinetic energy. This term represents the potential energy. Okay, so kinetic energy is related to speed, potential energy is related to, so this is related how fast it's going. So you can, if I have a nozzle, maybe got a nozzle that does this. So you're going to have a speed here, you're going to have a pressure here, you're going to have density there, and then you can have another velocity there. Pressure will be different, and the density probably is going to be the same. Okay, should be the same. So that's this case. Now, if I had the case, this is how the kinetic energy works, right? You got a flow, and there's a relationship between flow and the kinetic energy. In this particular example, the no gravitational effect, because your z, z1 is actually equal to z2, okay? So these also are equal. Why? Because if you just measure it about the same point, this is your z is not changing, okay? Now, if I had a case maybe that went something like this, you had a flow that did something like this. So now in this particular case, you have a velocity that's coming here. You're going to have a pressure that's coming here. You're going to have a rho that's coming here. You have a z that's coming here. And this also may be different in this location. Okay? 2, 2, and z2. Since all these are different, and you can see that there is a difference between there's a delta z there, right? So in this particular example, you will have the potential energy. Okay, so the couple more things to fix here before we move on to the Bernoulli equation. When this is the mechanical energy, you can write this as delta P over rho plus, let's write it down like this. P2 minus P1, V2 squared minus V1 squared divided by 2 plus G times Z2 minus Z1. So every problem depends on you locating what's your position 1 and what's your position 2. Okay, now your delta E mechanical is going to be bigger than 0. It's going to be bigger than 0 if it's supplied. If work is supplied to the fluid. Okay, and delta E mechanical is going to be less than 0 if work is extracted from the fluid. Okay? Okay? One last thing to keep in mind, if I wanted the total energy, let's say I don't call this, and I can find the total energy by simply multiplying by the mass flow times your internal energy per unit mass rate. Okay? Or if I wanted also, if I wanted to find just my E, I just had to multiply the mass times E. Okay, don't forget your mass is nothing else than rho times volume. That can be helpful. So these are some nice equations that are useful, handy as we move along. Okay, so let's understand this problem. Okay, let's see how this really works. Let's put it all together. So I want to know how much power I need here. But to find that power, I just need to have 2 points. I said point 1. I'm going to call this point 2. Okay, call this point 2. Now, what you can see is that point number 1. What do I have at point number 1? At point number 1, I have a mass. 1, and the mass is actually equal to m. Remember, because equation of continuity, it just tells me that mass has to equal to mass 1, has to equal to mass 2. That's just a given fact. What else do I have there? I know that the density is going to be rho, because just remember, it's the same fluid, and is not viscous, so the density will be the same as well. The another thing I know here at point that this location, this is 0, z1 is equal to 0. I know that you might say, hey, the 0 is there. We are just basically checking it down there. Okay, so then the velocity is basically 1. If you think 0 is basically steady, yeah, it gets speed, it speeds up here, but here at this point is 0. Okay, so let's go to point number 2. That will be this point at top. What do I have? I have a mass 2. That would be m dot. My density will be rho. My z2 will be this distance as h. My velocity 2 is basically constant. So it's very slow. It's moving very slowly. It's very close to 0 as well. Okay, so I have this from the figure, and that's what I'm going to decide. And also, from point 1 to point 2, there is no Q coming to the system or going out to the system. There's no work done in and out. This is from point 1 to point 2. Okay, so as I just mentioned, E is equal to m dot E. So E1 will equal to M1 times P1 rho 1 plus V1 squared over 2 plus GZ1, and E2 dot would be M2 dot would be P2 rho 2 plus V2 plus GZ2. Okay, so so as we move on, what we know is that what's going to come in is going to equal minus what's going to go out. That's your energy. It's all equal to 0 because of this. Okay, so if I replace all these values, note that this is m dot. This is m dot, right, from here. Also, I know that, I have my atmosphere. So at location P, my P will be, let's call it P. And my location here at P2, this is P atmosphere. Okay, because it's in the air, it's in the atmosphere. So at 1, this is P, this is rho, this is rho, this is P atmosphere. These are all 0. You can see it from here. These are 0. And then Z1 is 0. And Z2 is H. So this is G times H. So if I put it all together now, let's go to the next page. You see that you get M dot 1, M dot. So you have this, and all these are 0. So basically we have m dot p over rho. Everything else is 0 plus 0 minus second term. What goes out is m dot, and then this is 0 and this is gh, this is atmosphere. So this gives me m dot p atmosphere divided by rho plus gh is all going to equal to 0. Okay, so from the problem itself, then you can show that these two, I can combine them. M dot P minus P atmosphere over rho is going to equal to M dot GH. Okay, so I know all these quantities because I know what my G is, I know what my H is, I know those values because those values are basically are known. If you look at the problem, it's giving me what m dot is. This is all my m dot before it shows up here. The mass flow has to be the same. So I am basically saying that this is all going to be 2 kilograms per second. This is a 981 seconds squared. The h is 10 meters. So if you do this calculation, it gives you 196 watts. This is the power, actually. This is the maximum power, rate power. This is the maximum power that your engine is going to need, your pump is going to need to shoot this out on this side. Okay, so this is how we actually do these problems. And if you wanted to know what speed this is coming out here, then you do the same thing, but you go from 1 to 2. Okay, this is how these equations work. Okay, so with this said, let's go ahead and define a few more things that are important in the problem. One we call the mechanical efficiency. And this is very important, especially when you're doing turbine engine analysis. So the mechanical efficiency is important and is given by E mechanical out divided by E mechanical in. Okay, or another way to write this is 1 minus E mechanical loss divided by E mechanical in. Okay, this is how you define the pump. And this ratio, this is a ratio that is typically less than 1 and has to be at least less than 1. Okay, so this kind of gives you an idea how this works. So for an example, you also want to know how to calculate this for a fan, right? Because your turbine have your fans, and you may want to know how to do that. Well, if you wanted to know how to do that, then, but you can show to yourself what's coming in and what's going out for 1 and 2. You can show that your delta E mechanical, and you can actually do this, fluid, or the fluid, will be m dot v squared over 2. Okay, so this is what this is really going to look like, and you could do the whole actually you could do the whole equation if you wanted to. You can see this is all placed here, and your mass rate 1 is equal to mass rate 2. So if I use the same equations as before, just to show you, they will definitely get the same equation, same answer. You will get this answer. So E in, okay, what's going in? E1 is going to equal, it's the same mass, The pressure is the same, so let's call this P1 rho. Same rho is the same fluid, so rho is equal to rho. You have V1 squared over 2. This is 0, is given here, V0, plus G Z1, okay? And then E2 is equal to the same mass flow rate. P2 is equal to P1, so I'm going to call this P1. The velocity now, V1, V2 squared is not 0, plus, plus your G is equal to Z, but Z is equal to Z2. Okay, so when you take this minus this and you equate that to 0, just to flow around this, that will actually give you a value that will give you E1, that will give you a delta. So when you subtract, when you're subtracting 2 minus 1, final minus initial. So when you subtract this minus this, the only thing that you're left with, then you can say that you're, I'm sorry, this is your delta. Sorry, this is your delta E. Okay, this is your delta E. So then your delta E will equal to this minus this, and you will end up with V2 squared divided by 2. So this is expression I have here. Okay, and you want to divide this. The fan is this divided by the shaft, the power of the shaft. That's equal to 50. That's what's giving you there. That's the power that's generating. So therefore, divide by 50, and you're seeing that your fan turbine efficiency is about 72%. So that's what the equations really mean. Then you can also have the pump efficiency. You can have many other. You can have the turbine efficiency. If you wanted to do the turbine, the eta turbine is going to equal to the power of the shaft out divided by your delta E mechanical fluid. Okay, just the way we did it there. Just the way we did in this problem, right? This is the delta mechanical fluid. So this is this guy right here, okay? So here you just take it opposite, and you can also show this is the same as W turbine, the power that the turbine is generating, and the power that you really need in the that your problem is using, okay? Turbine E. Okay, so with that said, let's move on to the topic of Bernoulli. Bernoulli equation. Okay, just wanted to fix some ideas in space before we move on. Bernoulli equation is an approximate relationship between the pressure, velocity, and elevations. So think about this. It relates pressure, it relates velocity, and relates elevation. Okay, and this is valid. It's mainly valid over regions where this is steady. It is incompressible. The fluid is incompressible. Or although under some circumstances we may be able to use this for compressible, and your frictional forces are negligible. Okay, so this particular this is also, it ignores the viscous effects. And in this particular problem, we assume that the gravitational and the pressure effects sometimes are very small as well. If we, sorry, we want to consider that the viscous effect are very small when they're compared to this other, uh, when you have the inertia, gravitational, and pressure effects. So viscous effects are very small, so they can be neglected as well. So, uh, so the Bernoulli equation can be derived using either using energy conservation, or you can derive this using uh, momentum conservation. You can derive this using either one of these. Okay, so if I'm going to derive this equation, I am basically, I'm not going to derive it. I'm just going to give you the answer for this. So what you really have is the most general case for a steady flow along a streamline you're going to have the integral of dp over rho plus v squared over 2 plus gc, and this is going to be all a constant. Okay, the integral is only for this part right here. Okay, and if it's incompressible, remember, if it's compressible flow, then you have to use the methods that we discussed at the beginning of the class, right? It becomes even more cumbersome. We might do an example with that later, where this is equal to constant. So then this becomes, you can take this outside the integral. This is a p rho times v squared over 2 g times z is equal to constant. And you can see that actually this equation looks very familiar to you, and we have seen that in many different variations of it. Okay, so if there was the case in which you had unsteady compressible flow, unsteady compressible flow, then you can take the integral of p over rho plus the integral of partial of v respect to t over the area plus v squared over 2 plus gc is equal to a constant. Let's just put that integral there. Is equal to constant. Okay, so but we will not do many of those problems, but in the future, this is an area you like it, you know that this is the most general equation that you can apply for. It's compressible, then you remember the methods that we use in chapter 1, right, where you have to apply this, then you get the natural logarithm, you have to take the e on both sides, so the equations are not straightforward. You're going to just take this outside the integral. Okay, so to fix some ideas here before we do examples later on, there are limitations to Bernoulli equation. Okay, some limitation of Bernoulli equations, as I just mentioned to you, the flow is steady, it's a steady flow. So once you start the flow, you're not working, you're just waiting for it to be steady. So if you look at the airplane, right, you have an airplane, is taxiing here, is about to take off. So you can see that the Bernoulli equation will not apply here. right? This is no. It's going to apply mainly when you're in cruise speed, okay? And then once you start landing, right? Once you land in the airport, it does not apply in this segment. This is no. Has to apply where it's steady. And steady, you cruise speed. This is level flight. And there is no gust. There are no gust winds applied here. Okay. The second thing you have to think that I am assuming there is frictionless flow. What does that mean? Well, if you really think about the problem, right? Let's case in the case of the airfoil. Okay, I know that my flow is in contact here, and I know that I have friction there, right? So the Bernoulli equation is not applicable there. But as I move away from that, I move away over this stream over here. Then as I move away from that segment, that is applicable. Okay, it does not apply at the surface, but I can apply it in regions where there is a streamline moving. Okay, not a streamline that's in contact. Okay, so that is important. Let me give you a few examples that's worth to mention. These are sections where the Bernoulli equation is invalid. Okay, it's invalid. This is a no Bernoulli equation. Okay, you can see that here is expanding, so I'm going to have lots of friction going on here, so that's why there's a no. Here is a long and it's a narrow tube, so you can expect a lot of friction on top and bottom, so this is a no. Here and around the fan, you cannot apply it unless I take a big segment that's away from here. I take a boundary that goes like here, then I could apply it from here to there, but whatever inside doesn't matter. Then here it is, I'm heating it. Oh, you're heating. Heating means a no-no. You got a valve. Okay, now because you got a valve, now you're gonna have lots of friction. The boundary layer is a no-no. The wakes are a no-no. I can apply anywhere that's not applicable. Okay. The third thing that I have to keep in mind, it doesn't apply. There cannot be no shaft work. Okay, I'm working with the flow, not around the shaft. Has to be moving along the stream. So I got a particle, and the particle is just moving along here. Number 4, it is incompressible flow. Although we can expand this for uncompressible, mainly this is developed for constant. And you need to make sure that your Mach, remember your Mach was velocity divided by your speed of sound, has to be less than 0.3. So we can neglect the compressibility flows. Number 5, no heat transfer. Okay, there will be absolutely no heat transfer in these problems. Then number 6 is flow along a streamline. Streamline. So I'm saying if it's along the streamline, it is irrotational, if you remember. That's how we define the streamlines. Irrotational, it means that has no vorticity. Okay, so we are basically saying that your equation applies in case something like this. Okay, this is where everything applies. It applies at the point 1 and 2 that's going along the streamlines. Sorry. Okay, then so then the other thing that you have to keep in mind, if we take this same equation here, let me just copy this to the next page. This equation is important. This equation, so you got P over rho plus V1 squared over 2 and GZ. Okay, so in general, I could multiply this whole equation by rho, because I'm just multiplying by a constant, okay? So this is a constant. This is another variation of the same equation. And if we do that, then this part here is what we call static pressure. This is called static pressure. This part here is called the dynamic pressure. This part here is called the hydrostatic pressure. Okay, so in other words, the sum of all these pressures is called the total pressure. So the total pressure in my problem is going to equal to plus adding all these together. Okay, and this is the total pressure along a streamline. Okay. Okay. So we got those ideas fixed. Another concept that's very important and we use it very often, when I only add the static and dynamic pressures, that's called stagnation pressure. Okay, and the stagnation pressure, we typically express as P plus rho 2 squared. That's the stagnation pressure. And understand how the stagnation pressure really works. This is very important, but we use this a lot, especially for pitot tubes. So your airplanes have a pressure that actually measures the pressure, and we just measure at some point there. And at that point, at that particular point, your velocity that's coming there, I know what my pressure, my stagnation pressure will look like. This is what your gauge is measuring. So I could just subtract. I could find what my real velocity, my pressure is, or I can find what my velocity is going to be if I just take those. I take the difference of that. Okay, and that comes from this equation. You can see I can solve this. I could take this on this side. So I can take P stagnation minus P is equal to rho V squared over 2. Multiply both sides by 2, right? So this goes away. Divide both sides by rho. So this goes away. And now I take the square root on both sides. And this goes away. So that's where I get this expression. Okay, so this is what you need to know about the Bernoulli equation, and that concludes. That will conclude the talk on Bernoulli theory.